Abby White. I'm the project manager and structural engineer for OKAE Engineering. With me today are the other talented members of the OKAE Engineering design team. We have Katie Schreiner, our transportation engineer, Ellie McCulley, our water resource engineer, and Olivia Holtz, our environmental engineer. And to just give a quick project overview of the Amazon Industrial Park project, OKAE Engineering will be designing a Amazon warehouse facility as well as designing a new connector road from County Road 17 to County Road 19, as well as the implementing stormwater management practices and design of a new wastewater treatment facility. To give a quick recap on the structural project scope, the OKAE Engineering Structural Department will be designing an Amazon warehouse facility of approximately 50,000 square feet and will include spaces for office and reception areas, warehouse storage, equipment storage, packing and shipping areas, and auxiliary spaces. And currently, the structural department has been working on the structural framework layout, the evaluation of the preliminary design alternative, the selection of the preferred design alternative, and will continue with compliance with local building codes and regulations. The first alternative is a one-story steel structure. You can see all the way to the right is the current floor plan design for design alternative 1 and 2. It has an approximate area of 50,000 square feet and a perimeter of 900 feet. And the total estimated construction cost is $7,155,000. The image to the right is the first alternative structural framework layout for the floor system. We'll utilize a framework of steel beams, columns, and girders. As this is alternative 1's roof system, we'll utilize steel beams, columns, girders, and long span roof trusses to hold up the roof. This is the second alternative, which is a one-story reinforced concrete structure. You can see here that it has the same floor plan design as alternative 1, as it has the same square footage and perimeter of 50,000 square feet and 900 feet, but the total estimated construction cost is $9,064,000. And this is the second alternative structural framework layout. It will utilize a grid framework of reinforced concrete beams, columns, and girders. And this is alternative 2's roof system. It will utilize the same framework but have different spaces and span lengths and spacing. And we use the length to depth relationship to be able to determine how long the length should be and the spaces between members. This is the third alternative, which is another one-story steel structure. But you can see here in the floor plan design on the slide, it is a different design compared to the previous two alternatives, as the office area is now situated at the southeast portion of the building. Although the floor plan is a little bit different, it has the same square footage and perimeter of 50,000 square feet and 900 feet. And the total construction cost is $7,155,000. And this is the third alternative structural framework layout for the floor and roof system, and it will utilize a grid framework of steel columns, beams, and girders. And you can see here that it is illustrated as the girders are in red, the beams are in blue, and the columns are in the orangish little circle color. To achieve the project scope, we needed to evaluate 3 different alternatives: a one-story steel structure, another one-story reinforced concrete structure, and a one-story steel structure with a different floor plan. And this evaluation considered different key parameters such as construction cost, feasibility, environmental impact, space efficiency, and aesthetics. Here is the alternative evaluation rubric. Here we looked at the different key parameters and weighted it based on importance, scoring it from 1 to 5. And then we also took each alternative and then rated it from poor to excellent, which also received a score of 1 to 5, and then combined the scores to determine the best alternative for the warehouse. As you can see here, this is the structural ratings for each design alternative. We used the alternative evaluation rubric talked about in the previous slide. And alternative 3 has the highest total score among all 3 different alternatives based on the key parameters. And with this being said, the structural department of OKAE Engineering has selected design alternative 3, which is the one-story steel structure. to be the most preferred alternative for the Amazon warehouse, as it is tied for the lowest construction cost, tied for the least environmental impact, it's the most feasible design, and most visually appealing design. As well, it was second as the most space efficient. The total construction cost for the selected design is $7,155,000, and the total construction cost for the 20% contingency fee is $8,586,000. And you can see here in the table on the slide is the breakdown of each, the total construction cost for each alternative. And now I would like to pass the torch along to Katie to talk about the transportation portion of this project.
Hi everyone, my name is Katie Schreiner and I am a transportation engineer with OKAE Engineering. I'd like to start with reviewing our project scope for the transportation portion. So my major task for this project was to develop an expansion of County Road 4 going from County Road 17 to County Road 19. This roadway should provide access to the new warehouse that Abby has already described, and I'm also tasked with developing any and all parking structures. These elements need to be designed in accordance with the Indiana Design Manual, the AASHTO Green Book, and any Elkhart County codes and regulations. Included in my scope was a previously conducted traffic study describing how these new intersections are to be designed. So the first intersection is between County Road 4 and the toll road, and the Indiana Toll Road, and this is a signalized intersection. It has one lane that on the eastbound leg, there's one lane that is through and right turn and one right turn lane. The northbound leg has 2 left turn lanes and 1 right turn leg, and the westbound leg has 1 through lane and 1 left turn lane. Looking at the other intersection, that's between County Road 4 and County Road 19. This is stop controlled, which is a side street stop. County Road, it will stop for County Road 19 traffic, and since County Road 19 is out of the purview of our scope, there's going to be no adjustments made to that roadway, but County Road 4 will have a left turn lane and a right turn lane. Starting with a typical section of our road, County Road 4 will have 12-foot lanes, 1 lane in each direction, and a 10-foot shoulder. These lanes will have a 2% cross slope for the traveling lanes and a 5% cross slope for the shoulder to facilitate stormwater drainage into the ditches on either side of the roadway. In addition, we decided to use a hot asphalt mix design with a structural number of 4 as our desired value, and based on our mix we have a structural number of 4.1. We chose this number since this roadway will have a higher percentage of truck traffic. We want to make sure that the road is strong enough to handle this heavier loading. Moving on to parking evaluation, there are 5 main criteria that we are considering looking at our parking lots. The first is the number of parking stalls. Based on our estimates, we need about 45 car parking stalls for this lot. And then our next criteria was cost, comparing the alternatives to one another. Then the next two are site access and truck access, focusing on how easy it is to maneuver around the site and if it's how intuitive it is, and if trucks are easily able to move around. And the final is truck parking, making sure that there's enough stalls for the truck traffic that will be coming and going from the site. The first parking lot design has 3 parking lots, angle parking to the front of the lot and 90-degree parking to the side, and then truck parking will be located at the back of the lot along with the loading and unloading bays. This gives us a total of 87 car stalls, 34 truck stalls, a total square footage of 119,000 square feet, and an estimated cost of $844,000. This cost does include all striping, material costs, and a 20% contingency fee. Parking lot 2 has 2 parking lots, a 90-degree car parking lot closest to the roadway, and then the truck parking lot, again, behind the building. There's a total of 54 car stalls and 42 truck stalls for a total of 18,000 square feet and an estimated cost of $842,000, again with all the same cost criteria included into this. So based on the two alternatives, we decided alternative 2 is the best option for the parking layout. This number has a number of parking stalls much closer to the design value that we estimated, and it's much more intuitive in terms of navigating the site. Specifically for trucks, trucks are able to enter one side of the site, go down and unload behind the warehouse, and then exit through the other side, so they don't need to do a whole U-turn and move around and go out the same exit, as opposed to just doing one continuous loop around the building. Our roadway evaluation had 4 main criteria: alignment with existing infrastructure, the cost, intersection alignment, and environmental impact. We placed the greatest emphasis on alignment with existing infrastructure, since there isn't going to be enough traffic to prioritize one particular movement over another. And then intersection alignment is also a big priority here, making sure that there aren't any major curves as you're leading into the intersections, and getting as close as we can get to 90-degree angles. So just a recap of the roadway alternatives. Alternative 1 and 2 both have a roadway further south away from the wetlands, located on the northern end of the site, and the warehouse is on the northern end of the roadway. Alternative 1 prioritizes that alignment, as I talked about earlier, and alternative 2 is prioritizing that environmental impact, trying to reuse the existing infrastructure already seen on the site. Alternative 1 has an estimated cost of $1.9 million, and alternative 2 has an estimated cost of $1.4 million. Included in these costs are traffic control measures, so the signal and the stop sign, striping, and material costs, and the 20% contingency fee. Alternative 3 and 4 move the roadway closer to the wetlands and put the building to the southern side of the roadway. And alternative 3 again prioritizes that alignment I talked about earlier, and alternative 4 is trying to prioritize using that existing infrastructure. Alternative 3 has an estimated cost of $1.8 million, and alternative 4 has an estimated cost of $1.4 million. Based on this criteria, alternative 1 and 3 are our top 2 options, having a score of 38 out of 55 and 37 out of 55. And since alternative 1 does have the higher score, we decided this would be the best option for the site. At this time, I'd like to pass the presentation over to our Water Resources Engineer, Ellie.
Hi everyone, as mentioned, my name is Ellie and I'm the Water Resources Engineer for this project. I wanted to briefly go over the project scope for the Amazon Industrial Park. So first, we will be looking at minimizing storm water runoff and controlling flooding. And then second, we will be looking at treating the stormwater. Our primary goals within water quality treatment are 80% of total solids retained and 65% of total phosphorus retained. This will all be done in compliance with local and state codes, including the Elkhart County Street Standards and the Indiana Design Manual. And then finally, we are developing and evaluating different alternatives. So current work, we have completed a site evaluation and a volume estimation, including the water quality volume and flood control volume. And then we have picked and designed for design alternatives. Each of these includes a pond component primarily for that flood control, and then several water quality BMPs along with that to work on collecting those pollutants. We have estimated pollutant retention that will be presented with each alternative. These primarily came from the US EPA and Minnesota Stormwater Manual. And then we also have an estimated construction cost that goes with each of the alternatives. Finally, we'll look at alternative selection. These alternatives will be evaluated according to construction costs, TSS removal or solid removal, total phosphorus removal or TP removal, feasibility, and aesthetics. So alternative 1, we have a detention pond at about 48,000 square feet, permeable pavement, and vegetative swales, all coming to a total cost of about $362,000. As you can see, we have those vegetative swales right along the roadway, as well as within the permeable parking lot, and then all the water will eventually end up in our detention pond. Alternative 2 has 2 detention ponds, splitting the site into north and south ends. We also have a sand filter that is iron enhanced, a rain garden, and an infiltration trench, coming to about $265,000 in construction costs. As you can see here, we have, again, it's split into the north and south side of the site. So the water from the northern side will go through our sand filter and rain garden into this larger detention pond. And then from the south side, it'll go through the infiltration trench, landing in our smaller detention pond to the south. Finally, next we have alternative 3. This includes a retention pond of about 86,000 square feet, a green roof, floating treatment wetlands within that retention pond, and vegetative swales, all coming to about $1.8 million in construction costs. We have, again, these vegetative swales along the road. We have the green roof on our 50,000 square foot building, and then our retention pond with the floating wetlands inside. Finally, alternative 4, we have a detention pond of about 70,000 square feet. Again, a sand filter enhanced with iron and vegetative swales at about $356,000 of construction costs. Again, we have coming down these vegetative swales along the road, going into our iron enhanced sand filter, and then finally into our detention pond. Now looking at our evaluation criteria, we have 5 different criteria that we discussed earlier. These are each given a different weight, with construction costs weighted at the highest, and then TSS and TP removal weighted right next to it, with feasibility and aesthetics rated last. These will be multiplied by our ratings as we look through the different alternatives. Each alternative will be given a ranking 1 through 5 to then multiply by the weight to give our total score for each alternative. For this design, we have stormwater, which is very versatile, so rather than evaluating each alternative as a group, I will be looking at them in 2 different groups, the first group being the flood control or the ponds, and the second group being the rest of the stormwater BMPs. So first we have the detention and retention ponds. We can see here that the most cost-effective and best at removing is alternative 1. So that is the standard detention pond, and that is what we'll be using for our selected alternative. Next, we have broken down all of the water quality BMPs. This includes permeable pavement, vegetative swales, infiltration trench, sand filter, rain garden, green roof, and floating wetlands. Again, these were broken out into their own construction costs and their own removal efficiencies to be scored individually, and our top 4 are vegetative swales, infiltration trench, sand filter, and rain garden. So finally, our preferred or selected design alternative includes a detention pond, vegetative swales along the roadway, an infiltration trench, a rain garden, and an iron enhanced sand filter. I would like to pass it off to Olivia. So.
As mentioned, my name is Olivia, and I am the environmental engineer for OKAE Engineering's team. So just a little recap, the environmental project scope is designing a wastewater treatment facility for this Amazon project. And I would be in compliance with all regulations and standards, as well as the facility must be able to manage an average of 1 million gallons of flow per day, and then determining and developing alternatives. The current work thus far has been evaluating these primary treatment alternatives, and then choosing the selected and desired alternative based on different weighted criteria, and still being in compliance with all of the necessary code and regulations. So as a recap, my first alternative for the biological treatment aspect was using trickling filters. Just a reminder that they had low energy consumption and reduced odor generation, but the treatment efficiency was a little bit lower, which was something I noticed right away. And then the biofilm control is a little bit harder to manage, as well as the effectiveness decreases as the temperature decreases as well. So those are some factors to keep in mind. The second alternative was rotating biological contactors, and the pros to this one was that there were low energy requirements and provided a more compact design, but the treatment efficiency was about the same, 70 to 90% BOD removal. And then they do require routine maintenance, which will affect the cost, and then just a higher initial cost as well, which are some factors going into it that I was looking at. And then finally, my third alternative was using activated sludge, which is is the most common form of biological treatment in wastewater treatment facilities, with a high treatment efficiency of 85 to 95% BOD removal. Again, it's upwards of 90% of wastewater treatment facilities use this method, so it's very popular. However, it is sensitive to changes, and there is a high energy consumption that goes along with it. That being said, the parameters that were used to evaluate these different alternatives were cost, performance, effluent discharge, operation management, land needs, and time, based on a weighted scale, with 5 being the most importance and down to a 2 of least importance. And then using the evaluation rubric, which was also on a rating scale of 1 to 5, the score that was achieved was multiplied by the weight of it for a total possible of 100. So I decided to go with the alternative that received the highest score. So for the cost, I was looking for the overall cost being significantly less than the other alternatives, and then also with that, seeing even if it was maybe a little bit higher, if that price came with better options and better aspects of it as well, that made it more performance friendly. Otherwise then performance was the treatment efficiency being significantly higher is the goal. Effluent discharge was looking for the quality of effluent being discharged after this treatment stage, is that it was higher quality and the cleanliness was higher as well. Otherwise, for operation and management, it was looking at the amount of maintenance that could be required for each design alternative at a given time and how often it would need someone to be looking at it, as well as should the system have malfunctions, how difficult it is to take care of that and get it back running again. And then if anyone new comes into the facility or someone looking at these machines retires or leaves, how hard it is to train someone to be familiar with how to fix it. Otherwise, land needs, the space required would then go into the cost. So looking for a space, or land needs that were significantly lower than the others and more space effective. And then the total time needed to treat the wastewater going through this system, just that way it's not taking up a whole lot of time and backing up the system, and overall just the time it takes for that. So for trickling filters, it was given a 3 for cost because the initial capital cost was kind of lower average-ish, roughly between $2 to $5 million, and it requires periodic maintenance, so that is given for like the life. Performance received a 2. The BOD removal efficiency was reasonable, as mentioned before. It's less efficient and it's influenced by seasonal changes, which is hard to manage, especially in Indiana. The effluent discharge, it varies depending on operating conditions, so the amount of influent received and then just the quality of it as well coming in already. For operation and management, trickling filters are easy to manage. They're not very complex. Maintenance is pretty low as well, and every now and then it needs to be monitored and cleaned, but it's typically pretty good at not getting backed up or damage to it. Otherwise, land needs, they're typically larger or larger circular or rectangular beds, and these then require more land, which is going to take up more space and then overall going to affect the cost for it. And otherwise time, it could take longer to treat it due to the lower efficiency, but in the end it's not like a super long difference. For the second alternative, rotating biological contactors, for the cost, this one also had a higher initial capital, and then the mechanical nature of this adds to the amount that people need to be monitoring it and looking at it and making sure that everything is running smoothly. So with those in mind, the life is typically between 3.5 to 7 million. All of these are going to be specific to all the other factors in the treatment train, which is why there's such a broad difference between the low and high ends, which is something that will be monitored and developed further once the entirety of the plant process is completed. Otherwise, for performance, again, it's reasonable BOD removal efficiency. It is more efficient than trickling filters, but not quite as high as activated sludge, which kind of takes a hit for it. But the effluent discharge provides better quality effluent, but it's not as effective at meeting some more of the stringent discharge requirements. For operation and management, it needs more monitoring due to mechanical components again, and it is also more complicated to operate, so it did receive a lower score there. Otherwise, land needs, it takes up less horizontal space than the trickling filters do, as it's more of the vertical space, as you can see in the image. And otherwise, for the time, it's similar to trickling filters, but since it has a higher efficiency, it can lead to slightly faster treatment, which helps with the score there. And then finally, for activated sludge, the cost is roughly $3 to $5.5 million for the life, but that is just the higher capital and operational as well as energy and labor costs. But because of the high efficiency, it kind of overshadows the cost, which is what I mentioned prior. This is the gold standard for BOD removal. It's the most popular, so it has the high removal efficiency, so it's received a great score for that. The discharge then is high quality effluent. The BOD removal is very well done. It's ideal to meet any like discharge requirements and like the stringent responsibilities for it. However, for operation and management, it is pretty complex to operate and is difficult to understand like the ins and outs of it. It's not a very simple one to be able to maneuver, and any first-time entry-level people will kind of have a little bit of a difficulty understanding what all is required to it. But what's great about this one is because it's so common, there are a lot of people that will know about it. So even if it is this lower end, kind of harder to maneuver, there are a lot of people in the world and in the facility that will know how to maneuver around and handle that. Otherwise, for land needs, modern designs especially are very space efficient, and it can be more compact, so it's more efficient with less land area, which is really great overall. And then because the high efficiency, then the treatment time is also rather fast. So the BOD removal is pretty speedy, and then it gets through the rest of the process, so we're not kind of just waiting on this aspect. So then this is just kind of a chart showing all of the ratings and the overall calculations. And as you can see, alternative 3 being the activated sludge just have the highest score with 88, as opposed to trickle filters and rotating biological contactors that round out at 50 each. So for that reason, we have decided to choose alternative 3 activated sludge as the biological treatment process. So for the future, I'm just going to keep continuing to develop this chosen alternative and make it particular and especially focused towards our treatment facility for this Amazon Industrial Park project. And then looking at the rest of the treatment train process and all the other aspects that go with it before and after, and then just finalizing the size requirement that is needed for the overall plant and get that to the team. And then I would like to pass it back to Abby to round us out.
This is our updated phase 2 cost estimate, the design cost estimate for OKAE Engineering. Any questions?
Okay, Abby, I was impressed with your cost estimate in there, so can you tell me how did you get to the cost estimate to the nearest $2?
I used RSP square footage estimator.
So you actually accounted for every bolt and every connection in your building?
No, that is a phase 2 cost estimate. It will go more in depth in there. This was just a square footage estimator using the material and labor costs.
So why is it to the nearest $2?
I was just using the software. I'm sure.
Okay, good. So the second question for you, Abby, so how did you evaluate the environmental impact since you consider that as a criterion in your matrix?
I looked at it based on the carbon emissions, the energy used during production of each material, and the general life cycle cost of each material.
Okay. My next question is for Ellie, I believe. Simple question. So did you calculate the overall removal efficiency for your treatment train when it comes to water quality rather than flood control?
I did not. It's a bit difficult to accurately estimate the exact removal efficiency, just because some of them the water will go through one BMP to another one, so it already has a lower amount of pollutants than it started with, so those estimates are a little bit less accurate the farther down the train it gets. But we believe that this is going to be pretty much an overestimate of the amount of removal that is needed, just because each of the BMPs on their own nearly meet the requirements from the scope.
And the numbers you presented as percent removals, do they take into account the size of the units, the operation units in this case, the PMP?
Some of them do, some of them don't. It's the sources vary a little bit in terms of what they use to determine the efficiency rates. There were a couple of them that were based on the size of the BMP, but most of them just give a general range, and I took the average within that range.
Okay. Thank you, Olivia. It's next. So you started by saying that you're presenting your primary treatment, and then I see you migrated towards secondary treatment, like the biological treatment. So which is which in this?
You meant the biological treatment.
You meant the biological treatment, so you did not show anything about primary treatment?
Not yet.
Not yet. Okay, and just a clarifications in here. What's the difference between the effluent discharge versus the performance
Yeah.
of the treatment trade in this case?
So the performance is the overall like BOD like removal efficiency and the actual like number that goes along with that. Whereas the discharge is kind of looking at it more specifically being how ready it is to the next stages. So it is kind of a combination of both of them, but I did decide to separate it just because it could have a higher removal efficiency, but still not as great as like the overall like discharge than present.
And why is the time a factor, a criterion in this case?
In my opinion, I chose it as a factor requirement just on the off chance for like a storm or something where there's a lot more water, that it's not hindering the rest of the system and backing up everything else, and just kind of taking that into a factor in control, I guess I would say as well.
And since you mentioned that, did you account for the I&I component, since you mentioned in the store?
I did not yet. That is something that will be.
Okay. And just again for clarification in here, based on what you have presented, since you presented a big range of cost, gives me the impression that you did not actually size the units, at least do the schematic level type of sizing of the units. Did you, given you know your flow rate, you know your Q, and so for the different alternatives you have considered, did you do a schematic level type of sizing of the unit operations?
I'm planning to do that in the future. I was just kind of looking at the general to kind of give room for cushioning. And then once I actually determine the rest of the treatment train, from my research it's had found that it will also depend on the other aspects of the treatment train for this particular alternative.
So how did you come up with your best alternative if you do not do the sizing of the units?
I just used the general range that I could find.
It's more of the generic description.
Ellie, could you give me a quick summary of your selected alternative, I'm guessing, meets all the parameters that you had set as your goals. Do all of your alternatives meet all of those goals? Is that how you is that how you did it? You put together something that would meet all those goals and then decided which was
Yes.
cost effective and okay.
Yes, I do believe that every alternative does meet both the water quality and the flood control volume goals.
All right. And then Katie, I'm sure this is a slip of your tongue, but you said when you're talking about the asphalt mixes, the hot mix asphalt, you said hot asphalt mix, which would make it ham.
I was just thinking about lunch.
Yeah, okay.
My bad.
That's a good answer.
Very good, very good. I yield the rest of my time to Dr. Weiss.
Okay, so two questions for Ellie. So, just to, let's see. Your ponds, you had listed as 90% TSS removal. Is that dry pond?
Yes.
And so, which source said 90% for those? Because that seems kind of high.
I believe it was the US EPA, but I would have to look back at my notes to know exactly. But I know, I'm pretty sure it was the EPA.
Okay. And then your costs were just construction costs, right?
Yes, just construction costs.
Because, I don't know, maybe more of a comment, like infiltration trenches are high maintenance and really expensive. I'm not sure in the long run it would be that cost effective. So, you might want to reconsider that, or for design work you could still probably do it, but I'm not sure it would be, with all that open land and stuff, I'm not sure it would be cost effective in the long term. That's it. Okay, great.